Hello, this is Chapter 8, Basic Concepts of Chemical Bonding, Professor Kevin Mark. So we're going to put away, continuing Chapter 7, we're going to put away the calculator for a bit, talk about how to draw Lewis structures, its shape, polar or non-polar, etc. So as I mentioned in the previous slides, the valence electrons are the outermost electrons, those located on the outside, as opposed to the core electrons or the inner electrons. The valence electrons are important because it gives the element its particular chemical property. It also is important because of chemical reactions as well. So in general, you look down a group or down a column in terms of main group elements to let us know how many valence electrons there are. So for instance, chlorine is a halogen, group 7A, it would have 7 valence electrons. Sodium, which is an alkaline metal, will have 1 valence. I'll use this symbol, valence electrons. So as I just said, we look down the group. The trend here is 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, and 8. And there's no trend here in terms of valence electrons for the transition metals. So we will focus on the groups. So the question here is how many valence electrons are for magnesium. So we see magnesium here is in group 2, alkali earth metals. Therefore, it has 2 valence electrons. It has 12 total electrons, but again, there's only 2 on the outside that are involved in reactivity. And for instance, so Mg, as you know on the first level, 1s2, and then the next level, you can think of it as 2s2, 2p6, which is 8 electrons. And then level 3, 3s2 has 2 valence electrons. For krypton, it is a noble gas, 36 protons, 36 electrons. It has 8 valence electrons. So we introduced this electron dot system or dot symbol, and here we show again only the valence electrons. So we just mentioned that magnesium has 2 valence electrons, so you only show the outermost electrons, which is the 2 dots. Each dot represents an electron. For instance, we said chlorine has 7 valence electrons. In general, it has 17 electrons in total, but only 7 are on the outside. And you can draw the electron as a single electron or as a double, 2, but no more than 2, as we know intuitively we should only have 2 electrons in an orbital. So there are 2 types of compounds. We call ionic compound, which is between a metal and a nonmetal. And we have a covalent compound, which is a sharing of electrons between a nonmetal and a nonmetal. The ionic compound is usually between a metal and a nonmetal. So just briefly, a little bit about ionic compounds. We still want to maintain the octet rule, which means we want 8 electrons to be on the outside. And we'll talk about some examples in a few moments. There are some exceptions, of course, which we'll talk about later in the chapter. Also hydrogen and helium, they prefer 2 electrons on the outside. So as I said, there are the ionic compound and the covalent compound. We will focus on the covalent compounds in this chapter, where 2 nonmetals share electrons in a bond. So it's usually between a nonmetal and a nonmetal. We'll look at the most simple case of H2, hydrogen gas. The total valence electrons for hydrogen is 1, but there's 2 of them, so 2 valence electrons. I'll just say 2 valence electrons. So if we say H1 for the hydrogen on the left and H2 for the hydrogen on the right, we see at a certain distance the electron from H2 gets attracted to the nucleus, which is positively charged of H1, and vice versa. We have the electron in H1 being attracted to the nucleus in H2, and eventually they come together, and there's an ideal length, which we'll talk about in the lab, one of the Gaussian labs. So repulsion takes over, and then there's a nice medium to give us the bond length for H2. But just want to show you here, this is the Lewis representation of H2, where this line in between represents a bond, and it's a sharing of electrons. So again, we have the octet rule. We want each element to have 8. Some exceptions, as I said in the previous example, we have hydrogen and helium. Hydrogen only wants 2 electrons to be happy. So in this case, F2, we want to find the total valence electrons. If we look on the periodic table, fluorine has 7 valence electrons. It's a halogen, but there's 2 of them, so 2 times 7. We have a total of 14 valence electrons. So we have here, we need to use up our 14. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 2 of them are involved in the bond to make a total of 13, 14. So we used up our 14 valence electrons. So let's slide over to the picture on the right here. We have a bond here, which is made up of 2 electrons, sharing of electrons. We used up our 14. Now we want to make sure our octet rule is satisfied, meaning each element has 8. So let's look at the fluorine on the left. We have 1, 2, 3, 4, 5, 6, and 7, 8, because they share. And on the right, we have 1, 2, 3, 4, 5, 6, 7, 8. So each element has 8 electrons, so both are happy. And we used up our total of 14 valence electrons. Just want to point out, we have this term called lone pairs, just like a pair of socks, pair of shoes. A lone pair of electrons consists of 2 electrons. They are not involved in any chemical reaction. So here in our F2 molecule, we have 6 pairs of valence electrons. 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pairs of valence electrons. We can also have double bonds, which consist of, as the name suggests, 2 single bonds, and it's composed. A double bond is composed of 4 valence electrons sharing. So 1, 2, 3, 4. So in this case, carbon dioxide has 2 double bonds, and it has 4 lone pairs, and they're all on the oxygen. For nitrogen, this is a triple bond. Nitrogen N2 has a total of 10 valence electrons. Each nitrogen carries 5 electrons on the outside, and here we make a triple bond. And the general trend for bond lengths, a single bond is greater than a double bond, then greater than a triple bond in terms of bond length. So to draw a Lewis structure, I think we've touched on most of it already. The first thing is you need to figure out the total valence electrons, and what we need in front of us is a periodic table. If we were to have something like a plus sign or negative sign, so for let's say we have ammonium, which is NH4 plus, the total valence electrons here would be 5 from the nitrogen, 4 from the hydrogen, 4 times 1. But because ammonia is positively charged, we have to take an electron away. So the total valence electrons would be 8 valence electrons for NH4+. So we have the periodic table in front of us to figure out the total valence electrons. Step 2, we choose the central atom. For now, we'll use the idea that the one that needs the most valence electrons, the element that needs the most, will go in the middle. So for instance, CO2, carbon has 4 valence electrons. It needs 4 more to make 8. And for one oxygen has 6 valence electrons. It needs 2 more to make 8. So the one that needs more electrons to make 8 will go in the middle. So in this case, the carbon will go in the middle. If you recall the slide before, the carbon will go in the middle. Also, we know that hydrogen can never be in the middle, because if we were ever to have hydrogen in the middle, so if this is it, hydrogen's in the middle, we have a bond to the left and a bond to the right. We know this is not possible because hydrogen only wants 2 electrons to be happy, and when you have a bond to the left and a bond to the right, that's a total of 4 valence electrons, which means too many. Step 3, we draw a single covalent bond between the central atom and each surrounding atom, and then step 4, we place the remaining electrons on non-central atoms, called lone pairs, and then whatever is left over we put on the central atom. And if the 5th step, if we need to add double or triple bonds to satisfy our octet rule, use up our total valence electrons, etc. So here's one example, the phosphorus tribromide. I'll draw this, the phosphorus Br3. Phosphorus has 5 valence electrons, and bromine has 7, but there's 3 of them. So in total, there'll be 26 valence electrons. Bromine has 7 valence electrons, 1 bromine. It needs 1 more to make 8. Versus the phosphorus, it has 5 valence electrons. It needs 3 more to make 8. Therefore, the phosphorus will go in the middle because it needs more to make 8. I'll draw the bromine here. So we put phosphorus in the middle, bromine. Our total valence electrons is 26. And we have to make sure each one has 8. So let's put our 26, 1, 2, 3, 4, 5, 6, 7, 8 in the bond, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And we have to put 2 more on the phosphorus, 25, 26. When you draw Lewis structures, you should go by hand, use a pencil and paper, use an eraser because you use a lot of trial and error. So we used up our 26, I counted 26, and we see to make sure each one has 8. The bromine has 1, 2, each bromine has 1, 2, 3, 4, 5, 6, 7, 8. So each bromine has 8, and if we look at the phosphorus in the middle, we have, again, 1, 2, 3, 4, 5, 6, and 7, 8 on the bottom. So phosphorus is happy, it satisfies the octet rule, and each bromine has 8 as well. So try these examples, 1 to 7. I'll give you guys a pause the video, and we'll go over it in a second. So again, these are posted on the Common CUNY Blackboard site. The images that I drew, we can do a few. We can start with the water. The water has 8 valence electrons. total valence electrons. So that's step 1. 8, 6 of them come from the oxygen, 2 of them from the hydrogen. So we put oxygen in the middle because we said hydrogen can never go in the middle. We connect hydrogens on the left and the right. And then we count 8. Count 1, 2, 3, 4, and we place the remaining 4 above and below, 5, 6, 7, 8. At the moment, it's not important if the lone pairs are above or below. We just need to indicate there are 2 lone pairs. We used up our 8 valence electrons, and each element, in this case oxygen, has 8. Draw it in green. 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is happy. And for hydrogen, each hydrogen should have 2. Hydrogen here has 2, 1, 2, and 1, 2 here. So this is the correct Lewis structure for H2O. We'll do the odd ones here. So for CCl4, the total valence electrons for CCl4, 28 from the chlorine, 4 for the carbon tetrachloride, so it makes a total of 32. So we put the C in the middle. Carbon needs 4 more to be happy. Chlorine already has 7. It needs 1 more to be happy, so chlorine goes on the outside. Carbon goes in the middle. So let's attach. And now we place the 32 electrons. So let's do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'll finish on the bottom. 19, 20, 21, 22, 23, 24. And now we look at the bonds. 25, 26, 27, 28, 29, 30. 31, 32. So we used up our 32 valence electrons, and we have to make sure each one has 8. So I'll focus on the chlorine on the right. We have 1, 2, 3, 4, 5, 6, 7, 8. And each of these chlorines has 8. And we look at the carbon in the middle. It has 4 bonds, therefore, and each bond has 2 valence electrons. Electrons that are shared, so the carbon has 8 electrons as well, satisfies the octet rule. This is the correct Lewis structure for carbon tetrachloride. Let's look at another one. We can try NF3, number 2. NF3 has a total of 26 valence electrons. I'll let you do the work here. 5 from the nitrogen, 21 from the fluorine. Again, you need a periodic table in front of you. So the N goes in the middle. The fluorines go on the outside. And we need to make sure we use up our 26. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, and no count here, 19, 20, 21, 22, 23, 24, and I'll add 2 more on top, 25, 26 on the nitrogen. We count, we look at a fluorine, one particular fluorine, which has the one on the bottom, 1, 2, 3, 4, 5, 6, 7, 8, so the fluorine is satisfied. And we look at the nitrogen now. The nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So each element has 8 valence electrons, which satisfies the octet rule. Number 5, we'll try C2H2. Total valence electrons is 10. 8 from the carbon, 2 from the hydrogen to make 10. We put carbon in the middle. We put hydrogen on the outside. So let's say right now we used up 1, 2, 3, 4, 5, 6. We need to make 10. So let's put it on top. 11, 12. Sorry, we used up 6, 7, 8, 9, 10. We need to use up our 10. But if we look, this is not correct because the carbon only has 6 around each carbon. And we need how many? We need 8. So let's erase the 2 carbons, sorry, the 2 electrons on top and the bottom. We add a double bond here. So we still use up 10. 1, 2, 3, 4, 5, 6, 7, 8. No, we've only used up 8. We should add another double bond. Sorry, another bond to make a triple bond. So now we used up our 10 valence electrons. The hydrogen here has 2 electrons, so hydrogen is happy. Each hydrogen is happy. We look at the carbon. Look at carbon here on the left. It has 8 total valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Remember, these are sharing with the carbon on the right. So this is the correct Lewis structure for C2H2. Number 6, SCN minus. So the sulfur has 6 valence electrons. The carbon has 4. The nitrogen has 5. Plus you have a negative charge. So 6 plus 4 plus 5 is 15. Plus a negative charge, we have 16 valence electrons. The carbon needs 4 more to make 8. The sulfur needs 2 more to make 8. And the nitrogen needs 3 more to make 8. So the carbon will go in the middle. We connect S and the N. We must put a bracket sign around to indicate that it has a charge of -1. And let's start adding electrons. So we need to use our 16. We used up 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And here we see that the sulfur and the nitrogen only have 6 valence electrons. 1, 2, 3, 4, 5, 6. So this is not the correct Lewis structure. Let's try again with a different approach. Let's try a double bond. So if we have double bonds between the left and right, you used up 8. We need to add 8 more. So we'll add the 8 here on the sulfur. So we used up 8, 9, 10, 11, 12, 13, 14, 15, 16 to complete on the nitrogen. And now if we look, each element has 8 valence electrons. So this is the correct Lewis structure for SCN-. Number 7, which is ammonium ion. The total valence electrons is 8, 5 from the nitrogen, 4 from the hydrogen, but you have a plus sign, it's a cation, therefore you take away 1 electron. So the N goes in the middle, H left, above and below, H left to the right and above. Remember, hydrogen can never go in the middle. We have to put a bracket to indicate it's a positive charge. And if we look at this now, we used up our 8 valence electrons and the nitrogen has 8. So whatever you worked on, keep that work because we're going to use it in chapter 9 to identify the shape of our object or our structure, as well as the polar or non-polar. The next thing is formal charge. It's a way, so sometimes there are more than one way to draw the Lewis structure of a particular compound. So we introduced this formal charge. So the formal charge to distinguish which one is better. So it's the charge on an atom would have if all of the electrons in a covalent bond were shared equally. So the formula is to determine the formal charge on an element is valence electrons, which we find from the periodic table, minus the number of bonds minus all the non-bonding electrons, so the electrons in the lone pairs. So if we look at this structure, the silicon dioxide, here are two valid Lewis structures. Each one has 8. Each element has 8. The total valence electron, let's do this together. 6 times 2 for the oxygen is 12, plus 4 for the silicon. You need a periodic table in front of you. So that would be 16 valence electrons. So in this case, we used up 16 valence electrons for both structures. One of them is preferred over the other, and it's the one, so if you see in red, it's the one with the least formal charges. So the one on the left has a formal charge of 0, 0, and 0, and on the right, +1, 0, and -1. So comparing these two, the structure on the left with the 2 double bonds is the more preferred structure. How did we figure out it was 0, 0, and 0? Well, let's take a look. The oxygen on the left has normally 6 valence electrons. How many bonds on this left oxygen is 2, so -2, the number of bonds, looking at the formula above. And how many non-bonding electrons on this oxygen? There's 4. 1, 2, 3, 4. So 4. So not going to pull out the calculator, but we promised no calculators in this chapter. 6 minus 2 minus 4 is 0. We look at the central atom, the silicon. It has 4 valence electrons from the periodic table. There are 4 bonds, and there are 0 lone pairs or electrons that are not bonded. So this gives us a formal charge of 0. For the element on the right, it follows the element on the left and has a 6 minus 2 minus 4, again, to give us a formal charge of 0. Let's look at the compound on the right, which is a valid Lewis structure. If we look at the oxygen on the left, it's 6 minus 3 bonds, minus 2. 6 minus 3 minus 2 is +1. We look at the silicon in the middle, it's 4 minus 4 bonds, minus 0 electrons, so it's 0. And on the right, we have 6 minus 1. 6 minus 1 minus 6, because there's 6 unbonded electrons, which gives us -1. So this is an example of CO2. Just want to point out this is not the correct Lewis structure. I drew this structure just to give you an example how to figure out formal charges. So in this case, if we look at the oxygen labeled 1, it would be 6 minus 2 minus 4, which is equal to 0. We look at the oxygen above, which is 6 minus 2 minus 4, which is 0, equals to 0. We look at the oxygen on the right, which is 6 minus 1 minus 6, which is -1. And the carbon in the middle is 4 minus 5 minus 0 is -1. So two things to point out. Well, first thing is, again, this is not the correct Lewis structure because the carbon in the middle, if you see, has 10 valence electrons, and we want 8 for most elements. So that was the first thing. The second thing is we want to see here that the formal charges, -1, -1, should add up to the charge for the overall molecule. So -1, -1 gives us -2. So this was just an exercise to calculate the formal charge. One practice trial for you is to determine, using formal charge, the preferred Lewis structure for the following compound. So we'll draw each one. I'll write out the Lewis structure for each case. Total valence electrons is 16. So the one in the middle, the one on the right, are the lone pairs. So each one of these have 8 valence electrons for each element. We used up a total of 16 valence electrons. I'll quickly go through the formal charge for each case. For the structure on the left, it would be 4 minus 2 minus 4, which is -2. In the middle, it would be +2. 6 minus 4 minus 0 is +2. And on the right, 6 minus 2 minus 4 is 0. For the middle compound in red, we have here again -2, +2 for the oxygen in the middle, 6 minus 4 minus 0, and we have 0 on the right. And on the right, I'll go through step by step. 6 minus 2 minus 4 is 0. The carbon in the middle, 4 minus 4 minus 0, so 0 in the middle. And on the right, 6 minus 2 minus 4 is 0. So looking at the formal charges, they're all zeros on the right, so this is the correct Lewis structure. It has the least amount of formal charges. You could have also done this by looking at the fact that if you compare sulfur, oxygen, and carbon, the carbon needs the most electrons. It needs 4 more to make 8. Therefore, carbon would be in the middle.